Hello everyone. So welcome to my channel Hypermesh Basic to Advanced. To give an overview, I publish Hypermesh tutorials on this channel. So if you are new to this channel, you can check other videos on this channel. Okay. So one more thing, if you are already watching my channel, following my channel, it would be very helpful if you could subscribe to this channel, as it takes a lot of efforts to make these videos. So okay, without wasting time, let's start with the topic for today. So we are going to discuss how to perform frequency response analysis in Hypermesh using Optistruct. So for this tutorial, we will be using a circular plate with 5 holes, as you can see here on the screen. Okay. So I have already meshed this plate. Okay. So I have meshed this plate with 2D elements. Mixed type is mixed type of 2D elements. Okay. So next, after meshing this plate, we need to create the properties and material for the part. So I've already created the material, as you can see here on the left side in the white browser area. So I have used steel as the material. So this values EG and new values and row values for steel are by default present in this Hypermesh. So I've used this only. So next, going to properties. So I've used shell properties here. Okay, and I've used a shell thickness of 2. Fine. So what we are basically going to do is we are going to constrain these 4 holes on the periphery of this circular plate, as you can see here. So I zoom in. Yeah, so these 4 holes on the periphery of the circular plate, and we are going to apply frequency load on the center hole. Okay. So first of all, for doing that, we need to create RB2 elements. So as you can see, I have already created RB2 elements here. As you can see here, these red lines. Okay. So how you can create this RB2 elements? So for that, you can just go to 1D. You can see here 1D. Then you can go to rigits, and then you can select the nodes which you want to include in the RB2 elements, and your RB2 elements will be created. Okay. So next, after creating the RB2 elements for all the 5 holes, we'll constrain the 4 holes. So for that, you can just right click on this white browser area, go to create, and go to constraints to create a constraint. I've already created a constraint. So as you can see here, I already have a constraints load collector here. Okay. So we'll constrain this 4 master nodes of this RB2 elements of these 4 holes. You can see here. Just hide this. Okay. So if you can see, constraints for these 4 holes are already created. 1, 2, 3, 4, 5, 6. I have already constrained all the degrees of freedom for these 4 holes. So if you want to know how to create the constraints, for that you can go to analysis here, then you can go to constraints, and then you can select the nodes which you want to constrain and the degrees of freedom, and you can mention 0 if you want to constrain all these degrees of freedom. The load type for this will be SPC. Okay. So next, once we have constrained all the holes, we need to give the frequency input, right? So what will be this frequency load? So basically, what we are going to do in this analysis is we are going to subject this plate to a range of frequency, and we are going to observe its behavior within that range of frequency. So this is basically what is frequency response analysis. The subject or the part we are observing will observe its response to the frequency to which it's subjected, right? So next we need to create a constraint, a load collector. So that will be a D area load collector. Fine. So for that, again, we can just go to this white browser area. You can right click and go to create, and then we can go to load collector, and we can create a load collector. So the for this, creating this load collector, we can again go to analysis, and we can go to constraints, And here we have to select the master node of the central hole. Okay, and then we'll change the load type from SPC to D area. As you can see here, it's D area here. You have to select this. Okay, and then we have to select the direction in which this load will be applied. So for that, as you can see, this the perpendicular direction to this plate is the x-axis. If you can see here, the x-axis, right? So that will be a degree of freedom 1. Fine, and that is the reason you can see a 1 written here, because that is the direction in which that load collector is applied, D1. Fine. So, and we have to uncheck all the other degrees of freedom because we are only using this first degree of freedom, that is along the x direction. Okay. So next we have to create one more load collector, that will be a table D1. So what will be this table D1? So basically this table D1 defines the function which it will follow, the frequency input which we are giving. It will follow this table D1 function. So for now it's linear in both the axes, x and y axis. Okay, it can be log also, as you can see here in the drop down. For now it's linear for both. Fine, and then we have to input the data points inside table D1 num. As you can see here, if you just click on this, a table pop-up window will open, right? So I've used the value of 0, x as 0 and y as 1, and x as 1000 and y as 1. So basically this is a linear graph. Okay, so this is the table D1 load collector. Fine, then next we need to create a R load collector. So what is this R load collector? So R load collector, basically it's used to couple this uh, D area load collector and table D1 load collector. Fine. So as you can see here, we have to enter the excite ID. Under the excite ID field, we have to enter the D area load collector, and under the TV field, we'll enter the table D1. Okay. So now we have the meshed model. We have the properties and materials in place. Fine. We have constrained the holes. We have the D area load collector, the table load collector, the R load. Next, we need to create a frequency load. Okay. So how to create this frequency load is, as you can see here, I've already created the frequency load. So here basically what we have to do is we have to create a load collector and change the card image of the load collector to freqi. You can see FREQI. Okay, so this is a load collector used for this frequency load, applying the frequency load. So after that, there under the freq1 field, we have to enter F1. So what is F1? So F1 is the starting value for the frequency from where it will start the frequency. So suppose we keep the F1 as 0. So initially the plate will experience 0 frequency. Then we have the DF field. So what is DF? So initially the input frequency will start from F1, that is 0. Then it will increment by DF. So DF is the increment in the frequency for each step. So after that it will go from 0 to 5, then 5 to 10. So it will keep on going like that, and it will keep on going till NDF, number of frequency increments. So how many frequency increments or steps we will go? That will be 200 here as I've used. Okay, you can use any number you wish, and you can observe the results. So your results will just be a bit different from mine, but you can just play around with the numbers and see how it's going for you. Okay, so basically these are the load collectors which we have to create for frequency response analysis. Constraint is common for all the analysis. Apart from that, for frequency response, we have created some additional load collector, the D area, R load, and table D. Okay, so we have the meshed model, we have the material, we have properties, we have all the load collectors created, right? So the next step would be to create the load step. So again, the load step, I have already created the load step, as you can see here. So I've named the load step as frequency response. Okay, So 1 minute. Fine. So as you can see, the frequency response load step is here, and the analysis type here we have to select frequency response direct. Okay. So we'll select the analysis type as frequency response direct, and now under the SPC field we'll select the constraints as usual. Then under the D load field we'll select the R load, right? And under the frequency field we'll select the frequency load. Fine. So this is how we define the load step for the frequency response analysis. Okay, so we have the mesh model, the properties materials are there, load collectors are there, and the load step is there, right? So before that, before we go into running the solver, there's one more step. If we can just define the what outputs we want. Okay, so for that we can go to analysis again, and we have control cards here. If you can see, then we'll just go to here. So here we have the global output request, as you can see. So here we can select what outputs we want. Okay. So here I have selected displacement and stress. You can select other outputs also if you want. Okay. So displacement and stress are the outputs we want. So we have selected them. Okay. So we'll go to return again. Okay, fine. So basically we have all the things set up for the analysis. So component is meshed. Properties, materials, load collectors, and load steps. Okay. So next, we have the whole setup ready for running the analysis. And one more thing, just to observe the behavior of different nodes under this, we can just note the node ID and we can observe the behavior, which I'll show you next in the tutorial. Okay, so basically we'll just start to run the solver. So that for that we can go to analysis, then Optistruct, and as you can see here, the export options will select all, run options as analysis, and memory options will use as memory default. Okay, and then we'll just click on this Optistruct and click on yes here, and it will start running the solver. Okay, so once you click the Optistruct button, a pop-up window like this will appear, as you can see here. So this is the solver running. Here you have the message log, here you have the optimization summary. So here the number of iterations, convergence, and progress. So basically once the solver run is complete, here you will get a message in the message log saying the analysis is complete, and if there's any error, then the error will be written here, and you can check out what is the specific error. So we have to wait for a while till this run completes. So let's see, the progress is 66%. Okay, so we'll wait till it's completed. So as you can see here, the run is completed, and we have got the message log here, and we have the message analysis completed. Fine. So next we'll view the results. So for that we can go and click this results button. Okay, so here we have the hyperview window opened. Fine. So in this video we can view the results. As you can see, we can just visualize the results. So currently we have element stresses on display. Now we can change this to displacement here. Okay, click on apply. Okay, so as here you can see the like you can visualize the displacement here. So currently we are in load 8, that is frequency is 35, right? So we can just change this and we can see if this is changing. The displacement of the part is changing. So let's say we got 164 suppose. So yeah, so there's a slight change in frequency. Previously it was 8.35, it's now 8.85. So there's a change in displacement with the frequency increasing, although it's very less. Okay, so we'll just go to one more and we'll see if it's changing further. So 196 suppose we will take, and yeah, so it has changed again. It's gone to 9.09 from 8.85. So yeah, it's basically the displacement is increasing with the maximum displacement is increasing with the increase in frequency to which the plate is subjected to. Okay, so this is basically how the plate will behave when it's subjected in that frequency range. Right? Then we can also check the element stresses here. Okay, so we can just select element stresses and click on apply. Okay, so we have this at 196. There's a peak stress of 2.575 Newton per minus 1. So let's see. It's reducing, frequency is reducing. Is there any stress change? So select the default. Yeah, so there's a change in peak stress at 2.375 Newton per minus 1. Fine, so stress is also changing with the change in frequency. Right? So this is basically how you can perform the frequency response analysis and the results. Right? So now what if you want to view the result in a graphical form? So for that I have also opened one more window here. As you can see, we have a hyper graph here. So this window is called the hyper graph window. Okay, so I'll just click on this window. Fine. So to visualize the results in this, what we basically do is we observe the behavior of the part, object, or node or element in graphical format. Fine. So for this also you will load the H3D file. Okay. So the x-axis I have kept as frequency, y-axis you can select either displacement or element stresses. Okay, fine. So next we have to okay. So next we have to select the node number. So we have N1, N2, N3, N4, N5, everything. So suppose we just pick some node. So suppose we pick 1466. Okay. So node number 1466 we have chosen, and we'll select the magnitude along x direction, and we'll just click on preview, and you can see the graph here. So the reason I selected magnitude along x direction is, if you can remember, the x direction was perpendicular to the plate, right? So we can just check this preview and we can see if there's something in the y direction. Okay, y direction also there's a graph. So but the values might be different. You can see here. So it's going from 0 to 1000, and the peak is 1.5 into 10 to the power minus 23. For the x case, what's the value? So it's a different value here in case of magnitude along x. Okay, so we'll just click on apply and see. Okay, so the displacement is increasing with frequency, as you can see, which we also observed here when we changed the frequency. The displacement here was changing, right? So that is what you can see here. Okay, so what will happen is basically it will keep on increasing, and it will just reach peak frequency, then it will fall again, and then it will again go up and it will find another matching frequency, and then it will again come down. So this is basically how this works. Okay? So basically, where there's a peak frequency is the frequency. Where there's a peak displacement at the frequency, that is basically a problematic frequency. So we have to take care of that, and it's better if a part doesn't reach that peak displacement at the frequency and it's out of the range, out of the operating range, right? Okay, so okay, this is all for this video. So hope like this video, you got to learn something new, you understood some new things, got to learn new things. Okay, so Next, I'll try to bring up a new topic. So this is all for this video. Hope you liked. So if you got to learn something new, you can just like, share, and subscribe. And that would be very helpful. Okay. As I told in the starting of the video, it takes a lot of time and effort to make this video. So thank you. See you all in the next tutorial. Bye bye.